Now we're going to see that a concavity argument can give us an alternative to the first derivative test to test critical values and decide whether it's a local maximum or local minimum. So as we have seen, to apply the first derivative test, you want to know where the first derivative is positive or negative. In other words, you have to solve an inequality. And that can be a little bit more intricate than just plugging a value in a function. So a shortcut in some cases is a second derivative test that uses a concavity argument. So let's try to see what that says. Let's say we're in the case where we have a critical point C, where C is critical because the derivative is 0. So this argument is not going to apply to the case where the derivative is not defined at C. So we have a critical value where the derivative is 0, so we have a horizontal tangent. And let's assume we're in the case where the function is twice differentiable and the second derivative is continuous. Then, if the value of the second derivative at C is positive, by continuity it stays positive on some small interval around C, and therefore the function is going to be concave up on some small interval around C. That means that the shape has to be something like that. Right, because we have an horizontal tangent at C and it's concave up near C, so we have this type of shape, and therefore we have a local minimum at C. Similarly, if the second derivative at C is negative, by continuity of the second derivative it stays negative on some small interval around C, and therefore we have this type of shape, and we can conclude that we have a local maximum at C. So to summarize, the second derivative test, which is again a way to test a critical value and decide whether at this critical value the function has a local maximum or local minimum. So this applies only to critical values where the derivative is 0, and only in the case where the function f is twice differentiable with a continuous second derivative. And we have observed that if the second derivative at C, so here we're not solving an inequality, we're just plugging the value C inside the second derivative. If we obtain a positive number, then f has a local minimum at C. If we obtain a negative number, then f has a local maximum at C. Of course, the natural question is what happens if we obtain 0 when we plug C inside the second derivative. In that case, no conclusion can be drawn, and we have to go back to the first derivative test. So to illustrate this third point, that the test is inconclusive in the case of a second derivative equal to 0 at the critical value, consider the function x to the fourth. Then the first derivative is 4x cubed, and this is 0 only when x is 0. Therefore 0 is the only critical point. The second derivative is 12x squared, which is 0 at 0, so we're in this third case. Notice also that inflection points are where you have a change of concavity, and of course this is often going to happen when the second derivative is 0. But this is not the criterion for an inflection point. You see that here we have no inflection point at 0, even though the second derivative is 0 at 0. This is because the second derivative 12x squared is always non-negative, and that means it doesn't change sign, and therefore the concavity does not change. Right? The concavity of the function is concave up on both sides of the critical value 0. Now, if we go back to the first derivative test, we need to use the sign of the first derivative. The first derivative here is 4x cubed, so it is positive for x positive and negative for x negative, which tells us that the function f is decreasing on the negative reals and increasing on the positive reals, and therefore at 0 we see that we have a local minimum. But if instead of x to the fourth we took negative x to the fourth, 0 would still be the only critical value, and the second derivative would be negative 12x squared, so it still would be 0 at 0. On the other end, looking at the first derivative test, well, we have the opposite derivative and therefore opposite sign for the derivative. It is positive for negative x and negative for positive x. Therefore, the function is increasing on the negative reals and decreasing on the positive reals, and we get a local maximum at 0. So you see that with a second derivative being 0 at the critical value, this critical value could correspond to a local minimum or to a local maximum. It could also correspond to neither. Just look at the case of f of x equal x cubed, which we have already used as an example of the fact that at a critical value you may not have a local extremum. For x cubed, the first derivative is 3x squared, second derivative is 6x, therefore it is 0 at 0. So we're again in this type of cases, but you see that you have neither a maximum nor a minimum. Now let's turn to an example where we can apply the second derivative test. We're looking for the extrema of the local extrema of the function 4x squared minus x to the fourth. Because we are not asked to find the intervals of increase and decrease, then we may want to use the second derivative test as a shortcut. Of course, if we wanted to have also the intervals of increase and decrease, there would be no point in using the second derivative test, because the first derivative test would apply straightforwardly after we find the intervals of increase and decrease. Okay, so let's say we just want the local extrema. We know that they can only occur at critical values, so the first step is to find the critical values. To this end, we find the derivative, which is 8x minus 4x cubed, and try to find the zeros of the derivative. So the derivative here factors as 4x multiplied by 2 minus x squared, and 2 minus x squared is going to be 0 either at positive root 2 or negative root 2. So we have three critical values: negative root 2, 0, and root 2. Now we're going to use a second derivative test to test each one of these critical values and decide whether at this x values the function has a local maximum or a local minimum. The second derivative is 8 minus 12x squared. The second derivative test allows us to decide if a critical value gives rise to a local maximum or local minimum in terms of the sign of the value of the second derivative at the critical value. So we plug in the second derivative negative root 2, 0, and root 2. At 0 we obtain 8. It's a positive value. That means near 0 the function is concave up, and that means we have a local minimum at 0. To get the minimum value, as usual, we plug 0 in the original function f, and in that case we get 0. Testing the other values, if we plug either positive or negative root 2 in the second derivative, we plug it in the square, we get 2, so we get 8 minus 24, negative 16, we get a negative value. That means near these values, positive or negative root 2, second derivative is negative. In other words, the function is concave down, and that means we have local maxima at positive root 2 and at negative root 2. And the value of this local maxima is the value of the function at negative root 2 and positive root 2, which happens to be the same in this case. If we plug either positive or negative root 2 in the original function f, we get 4. So that illustrates how to use the second derivative to test the critical values. Now we are going to return to what we were talking about before, which is curve sketching.